Picture this, you're standing at an old steel bridge in Pittsburgh, watching workers bolt massive beams into place. It's 1989, and engineer Harold Morrow is scribbling furiously, calculating forces and stresses without a scrap of calculus. How does he ensure this giant structure won't crumble under the weight of thousands of cars? That's where the secrets of statics and strength of materials come in, but what makes these principles reliable even decades later? Let's crack that code. First, we dive into the dance of forces acting quietly around us. Understanding how they combine and balance unlocks why buildings stand tall or collapse. Back in the early chapters, Morrow uses a classic example from a small-town armory. Two ropes pull a hanging cannonball at different angles. By graphically adding their forces, he shows how these combine into one single, resultant force exactly balancing the weight. It's like seeing teamwork in action, pulling together to hold something steady. Think of equilibrium like a tightrope walker balancing a pole. Every force, gravity, rope tension counteracts the others just right so nothing tips over. Morrow's neat diagrams transform these abstract ideas into a tightrope crossing where every step counts, making it obvious when forces harmonize or threaten collapse. When engineers in Pittsburgh applied these principles in 1989, they weren't just trusting paper theories. Stress measurements and load testing on the bridge confirmed equilibrium in action. That's the magic. Equations on the page that predict what steel and concrete will really endure, saving lives and money. Next, you'll see what happens inside materials when forces push, pull, or twist, a moment where physics feels personal and oddly poetic. Morrow tells the story of a railroad engineer testing steel rails in 1990 Ohio. By applying axial loads, forces along the line of the rail, they measured how the metal stretched, recording tiny millimeter elongations to gauge strength. This vivid moment shows statics isn't just math, it's real muscle and steel flexing under everyday stress. Hooke's law is like a spring's honest confession. Stretch it and it pushes back proportionally up to a point. Visualize a diving board bending under your weight. The more you press, the more it resists, snapping back when you jump off. Morrow uses this elegant analogy to reveal how elasticity governs not just springs but entire buildings. This understanding propels engineers from tiny tension tests to designing skyscrapers and aircraft wings. Recognizing the limits of elasticity means structures can absorb stress without breaking, a safety net for everything from bridges to your morning commute, all grounded in Hooke's simple formula. Finally, meet the hero and villain of structures, beams. How they bend, bear loads, and resist breaking turns out to be a story full of twists and surprises. Imagine a wooden beam bending under a stack of books in a university lab circa 1993. Morrow walks us through how bending moments create tension on one side and compression on the other. It's like a seesaw in slow motion, with the center line bearing the brunt of forces. This vivid setup makes invisible stresses suddenly clear and urgent. Shear forces act quietly inside beams, slicing parallel planes like scissors. Morrow compares them to playing cards slipping in your hands, not obvious at first, but enough to cause fractures. Recognizing shear's subtle damage is a breakthrough that prevented countless structural failures decades ago. Mohr's circle, no, not a fancy party trick but a geometric tool, distills complicated stress combinations into circles and angles you can visualize. When engineers use it, they predict exactly when materials will yield or snap, translating math into a crystal-clear map of strength and weakness. It's the ultimate cheat sheet for structural safety. Remember that Pittsburgh bridge, held steady by invisible forces you now understand? Every bolt, beam, and calculation came from these fundamental principles: equilibrium, elastic limits, and hidden stresses revealed by Mohr's circle. Next time you walk across a bridge or lean on a table, try spotting these forces in action. It's a fresh way to see the strength in everyday things. Subscribe for more book summaries like this one.